Okay. Well, you know, somebody said the sum of the J components has to be 0. And I said, I don't see anything in the principles that ensures that. Is there something we've left out? Okay? Well, we have Newton's first law, Newton's second law. Second law really applies pretty directly. In the J direction, there's no acceleration. This thing keeps moving in the X direction. Matter of fact, it's at rest in the J direction. And when I asked somebody to state Newton's first law, I said, well, an object at rest, well, that's okay if you qualify that. An object at rest in an inertial reference frame will remain at rest unless acted upon by an external force, right? But more generally, an object in any reference frame will have an unchanged velocity, meaning unchanged direction and speed, unless acted upon by an external force. And then Newton's second law tells us what to do with that external force. Okay? Okay, so now applying these principles, Newton's second law says sum of the forces is mass times acceleration. Now we're not going to calculate an acceleration because, except for the interval between 2.7 and 3 centimeters, we don't have any information at all about this magnetic force. Okay? But we do have information that can lead us to some conclusions about the magnetic force in that interval. We won't get specific magnetic forces, but we can get the average magnetic force. Okay? But that's going to be, it's going to take us a little while. So we have net force, which is the sum of all the forces equals mass times acceleration, right? So I'm just going to use N for normal. So this equals mass times acceleration, doesn't it? Okay? Now what do you know about the acceleration?
It's negative.
You don't know that. You don't know where this thing is. Okay? If you're close enough to the magnets, it's positive. If you're out away from the magnets and coasting, yeah, it'll be negative because the x direction is this way and we assume the magnetic force is this way and motion is this way, right? Something much more important. Acceleration's a vector. What can you tell me about this vector?
It's going in the I direction.
Yeah, there's no component in the j direction. Okay, we know that from our experience of this thing. We also know that from the fact that there are only two forces in the j direction, right? And one of them is in response to another. This one is in response to this. And it's an elastic or compressive force due to what this thing is doing to this surface. Well, it means when the surface rebounds, the force is going to be in this direction. Normal, right? So this force is in the direction opposite this one. Okay? Not always in the direction opposite this one, but because the plane is perpendicular to this one, this is going to be perpendicular to the plane. In this case, the plane is horizontal, right? All that. Okay, so we have mass times acceleration. We also know we could write the net force as A sub xi plus A sub yj, right? And why is A sub y 0 again?
Because it's not accelerating up or down.
Well, this force will be equal and opposite to this force, right? For a lot of reasons that you want to understand in depth, so you don't get confused when the situation gets more complicated. But right now, we'll go with this, right? Okay, so, well, we don't have room to write the rest of it here, so we'll do this. Thus, Fnj, yj, because the force is perpendicular to the surface, not because the weight is acting down, right? Surface is level, surface is in the x direction, perpendicular to that is the y direction, and it is in this direction because it's a response to this, right? Notice I don't say reaction. This is not an action-reaction pair. In an action-reaction pair, the source of the force is the same for both forces, okay? Well, one of these forces is gravitational, the other is not, okay? So it's not an action-reaction pair, but it's still a response to the compression and bending of the surface, okay? Okay, so anyhow, you got normal force times J, and the frictional force is minus mu times the normal force times I, plus F magnetic times I, where here I've got an arrow over F magnetic, right? So it's a vector, but now I don't, so it's the magnitude of that, but it's times the I vector because we're assuming it's in this direction, okay? Minus mgj equals m ax I. Okay? So there is the equation that embodies Newton's second law in this case. Make sense? Okay, what do we do with that equation?